To carve a complex V12 engine block from a solid billet of aerospace-grade metal, you must rip away 80% of the starting material. That requires immense, violent force at the cutting edge. This collision generates a massive surge of thermal energy. Every time that cutting edge shears a piece of raw stock, it ejects a superheated metal chip. Listen to the machinists programming these cuts, and their obsession becomes obvious. As one Seco Tools engineer put it while watching this exact process, heat, 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 heat up here. In manufacturing, the speed at which you carve away metal is called the material removal rate, or MMR. While many focus on spindle horsepower as the primary constraint on MMR, thermal accumulation sets the actual ceiling on metal removal rates. If heat builds up faster than the system can shed it, the results are catastrophic. Either the carbide cutting insert melts and shatters, or the heat soaks into the billet, warping the metal and ruining the engine's tight dimensional tolerances. To solve this, machinists use a specialized subtractive technique called high-feed milling to rough out the engine block. High-feed milling works by manipulating the physical geometry of the cutting tool. It is a mechanical strategy that manages thermal loads to maintain high productivity without destroying the tool. To understand how this works, we need to zoom in on the exact microsecond a cutting edge strikes raw metal. This diagram shows a standard 90-degree milling tool engaging a workpiece. Right at the point of contact is the shear zone. This is where the kinetic energy of the spinning spindle is converted into thermal energy to tear the metal structure apart. With standard machining, the heat generated at this zone has 3 places it can go. It conducts down into the workpiece, into the tool insert, and out into the chip. Heat often bleeds heavily into both the tool and the raw material. If you run this tool faster, that heat builds up rapidly. The 90-degree geometry of this tool also dictates how it directs physical force. Look at the force vector diagram overlaid here. As the 90-degree edge hits the metal, the primary resistance pushes horizontally, directly away from the cut. This is called radial force. If a programmer increases the feed rate, that horizontal radial force spikes. The tool shaft will physically bend and deflect away from the metal, ruining the dimensional accuracy of the part. This creates a strict trade-off. Cutting slow protects the part but wastes machine time, while high feed rates destroy the operation through thermal soak and radial deflection. Escaping this trade-off requires a geometric solution, drastically altering the lead angle of the cutting insert. This side-by-side comparison shows the difference. On the left is the standard 90-degree tool. On the right is a high-feed tool. The key difference is the high-feed insert's extremely shallow lead angle, typically 10 to 15 degrees at the cutting edge. That slight geometric taper alters the mechanical physics of the engagement. Watch the force vector shift. Because the angle is shallow, the horizontal radial force shrinks. In its place, a vertical axial arrow grows, pointing straight up. Redirecting the cutting energy vertically is highly advantageous for a CNC machine. The Z-axis and the spindle itself are the most rigid structural components on the entire platform. They are built to absorb immense vertical compression. By sending the force straight up into the spindle, horizontal deflection drops. The tool stays rigid, holding true to the programmed path even under heavy loads. By shifting the force into the machine's strongest axis, engineers provide the physical stability required to push the tool far beyond standard limits. Stability only solves the mechanical problem. We still have to address the buildup of heat. This is where a phenomenon called radial chip thinning comes into play. It is a necessary consequence of that shallow lead angle. This close-up compares the chip formation. The shallow 10-degree lead angle spreads the removed material over a longer section of the cutting edge. The resulting chip is significantly thinner than the one produced by the 90-degree tool. If a chip gets too thin, the cutting edge loses its bite. Instead of shearing the metal, it rubs against the surface, creating massive friction that destroys the carbide insert. To maintain the required minimum chip thickness, the CNC programmer must move the tool forward at a drastically higher speed. That mandatory high feed rate serves as the primary system for managing heat. This thermal gradient map shows the high feed tool in action. Because the tool is advancing so quickly, it spends only fractions of a millisecond in contact with any single point of the workpiece. This prevents the thermal energy from conducting into the block.
The rapid advancement ensures the heat is carried away by the material being removed. Red-hot chips are continuously ejected, leaving both the workpiece and the tool insert relatively cool. The high feed rate functions as a thermal evacuation mechanism. It ejects heat from the cutting zone before it can soak into the engine block. Applying these microphysics to the massive billet reveals the logic of the process. Carving this engine block requires thousands of rapid passes, sending a heavy torrent of metal chips continuously out of the cutting zone. Removing 80% of a solid block creates an immense matrix of thermal stress. If the heat were allowed to settle, the engine would twist out of tolerance. The axial force vectors are absorbed by the spindle, while the thermal map shows the engine block remains stable by rejecting heat through the chips. Combining axial force redirection with the thermal evacuation of radial chip thinning ensures the block remains dimensionally stable throughout the roughing process. It is an elegant solution based on physical geometry, allowing for high productivity without relying on brute force alone. In high-tier subtractive manufacturing, true efficiency and extreme material removal are achieved by re-engineering the microscopic geometry of the cut to eject heat before